We're going to talk about buffers today. A buffer is a solution that is designed to resist changes in pH when a strong acid or a strong base is added. A buffer consists of a weak acid and its salt, which would be a conjugate base, or a weak base and its salt, which is its conjugate acid. So you need to be able to find out if two compounds will make a buffer system or not. Here we have phosphoric acid, and phosphoric acid has a conjugate base. When it donates its proton, what is left on the other side of the arrow, its conjugate base, reflects the donation of the conjugate of the proton, and so here it is. This would make a buffer system. This would not make a very good buffer system because this is perchloric acid that is a strong acid. By definition, its conjugate, or its leftover, is a very weak conjugate base, so it won't do a very good job of protecting the pH of the solution. Here we have an acid, the ammonium ion, and when it donates a proton, what is left is this weak base. This will make a good buffer system. So you take a weak acid and its conjugate base, or its salt, and you put it together in a solution. What happens, in this case it's acetic acid, is you have the acetic acid and it will dissociate to some extent, forming a proton, which in water is the hydronium ion, and the acetate ion, and to it we have added sodium acetate, and it dissociates completely into the sodium ion and the acetate ion. It is now ready to protect against invading strong acids and strong base. The strong base, what we're worried about, is the hydroxide ion, and if a hydroxide ion is added to this buffer system, what we will have is the acetic acid combining with the strong base to make the acetate ion and water. Neither one of these will affect the pH of the solution much. So we have taken a potential threat to the pH and neutralized it by using the components of the buffer system. Now, like on the other hand, if we added a strong acid, the acetate ion would be attracted to this proton, and it would make acetic acid. And we know that acetic acid is a weak acid in equilibrium, and very little of this proton would dissociate. So we've taken the threat from a strong acid and mitigated its effect by having the proton join together with part of the buffer. And that's how this works. So we have just gone over that part. One of the things that you're required to do is to calculate the pH of a buffer system. You design a buffer solution to work in the pH range that you need. Your body has a carbonate buffer system that keeps your blood very close to an optimal pH range of 7.41. Let's say you had a solution that works, that you have a solution that you need to be acidic for a redox, for some sort of reaction. You would design a pH in the acid range, a buffer system in the acid range. You calculate the pH of a buffer using a derivation of the Henderson-Hasselbalch equation. The pH of your buffer is equal to the pKa. Remember, pKa is the negative log of the Ka of an acid. And then you take the concentration of the base divided by the acid, take the log of that, add those things together. This is a very easy way. Let's recall, even if you have a buffer that is basic, you are still using the Ka of the acid. Let's recall, to switch from Ka to Kb, we make use of the ionization constant of water, which is fixed at 25 degrees C to be this number. If you know it, oops, let's try to erase that. If you know one, you can calculate the other. There we go. All right, now let's talk just for a moment about the effectiveness of a buffer, how well it can work. A buffer will be effective if the ratio of the base to the acid is about 1. When you have equal concentrations of both components of the buffer, it works best. A buffer is most effective when the concentration of the acid and the base are between 0.1 molar and 10 molar. And a buffer will be most effective when the concentration of the weak acid and conjugate base, or the weak base and conjugate acid, are very large compared to the strong acid or strong base that we're protecting against. A buffer system can be overwhelmed by too much strong acid or strong base. The buffering capacity is defined as the amount of acid or base that the buffer can neutralize. The buffering range is the pH range for the buffer. A general rule of thumb is a buffering system can work in the range of plus or minus 1 pH unit of pKa. So if we have a pKa value that is 3.72, 3.74, our range of this effective buffer would be this. Okay. Let's calculate the pH of a buffer solution that's composed of 0.5 molar formic acid and 0.5 molar sodium formate. The Ka of the formic acid is 1.8 times 10 to the negative 4. So the pH is going to be equal to the pKa plus the log of the concentration of the base over the acid. It's your job to figure out which is which. Here's the acid, and here is its conjugate base. So our math would turn out to be like this. I get the pKa by finding the negative log of the Ka, and that would be 3.74. And then I took the molarity of the base with COOH minus divided by the molarity of the formic acid. That's 1. This drops out. So the buffer has a pH value of 3.74. Okay, it says that the buffered solution contains 0.25 molar NH3 and 0.4 molar NH4Cl. So here we have a base and its conjugate acid. Calculate the pH of this solution. The pH is equal to pKa plus the log of the concentration of the base over the acid. We are given the Kb value, and we see we need pKa, so I need to find the Ka, and that would be Kw divided by Kb, and that would be 1 times 10 to the negative 14 over 1.8 times 10 to the negative 5th. That gives me 5.56 times 10 to the negative 10th. The negative log of that value is 9.26. So 9.26 plus the log of the concentration of the base, 0.25, over the conjugate acid, 0.40, is equal to 9.06.